All right. Good morning, everyone. I'm Mariam Fazel, and it's my great pleasure today to welcome Professor Lucy Pao to the UW ECE Colloquium. Professor Pao is the Palmer Endowed Chair Professor in Electrical, Computer, and Energy Engineering at the University of Colorado, Boulder. She got her PhD in electrical engineering from Stanford University, and her research has focused on engineering control systems with applications that cover a broad spectrum ranging from things like atomic force microscopes to wind energy systems, which she will be talking about today. Her awards include the 2012 IEEE Control System Magazine Outstanding Paper Award, 2015 SIAM Journal on Control and Optimization Best Paper Prize, 2017 Control Engineering Practice Award from the American Automatic Control Council, Scientific Award of 2017 from European Academy of Wind Energy, and 2019 Nyquist Lecture Award from ASME. And she holds various leadership roles in important professional societies like the IEEE Control System Society, Board of Governors, and IFAC Executive Board. So with that, welcome Professor Lucy Pao, and we are happy to hear the talk.
Thank you so much for the great introduction. So it is a pleasure to give this talk. I'm sorry I don't have the opportunity to visit your beautiful campus and city, but hopefully the virus will recede soon and we'll get to see each other not too far from now. So as Professor Fazel mentioned, I will be talking about design and control of extreme scale wind turbines. I am at the University of Colorado Boulder. These are aerial photos of our campus and of the engineering center. I haven't been there for a couple months now. This is a larger aerial view, and I suppose if we're sheltering in place, this is not a bad place to be. So what I thought I would start off with is to talk about wind energy more generally, and then get into the discussion on design and control of wind turbines. So the data that I'm presenting here is largely from the 2018 Wind Technologies Market Report, and that was published last year in August, and the 2019 report will come out this year in August. So the kind of confirmed official data only goes through 2018 here. So I look at a 10-year period from 2009 to 2018. And over that decade, the global installed wind power capacity grew at an annual rate of about 17%. And I think it's pretty safe to say that in 2020 now we're beyond 600 gigawatts of installed wind power capacity worldwide. The number one country in terms of installed wind power capacity is China, and they've had an incredible annual rate of growth of about 36%. US is actually number two, and we've had an annual growth of about 15%. So together, China and US have more than half of the world's installed wind power. Now, another way that we can compare countries in terms of wind energy is to look at wind penetration. And here what we mean is the amount of a country's electrical energy needs that is being met by wind. And in this regard, Denmark is by far the number one country. So in Denmark, 40% or more than 40% of their electrical energy needs is met by wind energy. And this is an average across a year. And so they do instantaneously hit 100% wind penetration at times, in which case they're trying to export their wind power to nearby countries. So in general, European countries do quite well in terms of wind penetration. China, for all its installed wind power capacity, actually is only at 5% wind penetration. So they have a very large population, so large electrical demand, and only 5% wind penetration. The US has lower population, but we tend to be energy hogs, and so we only have about 6.5% wind penetration. But the point here is that there is a lot of room for growth. Now, I thought it might be fun to look by state, and in terms of installed wind power capacity, Texas is by far the number one state. In Colorado, we're not doing too badly. We're ranked 8th, and Washington State also does pretty well. You're ranked 11th. Now, if we look at wind penetration, Kansas is the number one state, and Iowa also has more than 30% wind penetration. So Colorado and Washington State do relatively well in the top 20. Now, if we look at the wind map of the US, we can understand why there's so much installation and high wind penetration in the center of the country, because there's just really great wind resource there. If we look carefully, we actually see that there's very good resource just off the coasts. Right now in the US, there's only one relatively small commercial offshore wind farm just off the coast of Rhode Island. So there's a lot of potential for growth in wind energy in terms of offshore for the US. Now, how does wind energy work? So in a nutshell, essentially wind comes into the rotor plane, and due to the aerodynamical design of the blades, that wind coming into the rotor plane creates lift that causes the rotor to spin. This spins the low-speed shaft. This speed is typically stepped up through a gearbox to a high-speed shaft. So it spins the generator then and generates electricity. That electricity is put on the grid, transmitted out to users. Now, this is a typical three-bladed upwind turbine configuration. That's the most common type of commercial wind turbines there are. Now, on the back of the nacelle, there are these sensors, the anemometer, which measures wind speed, and the wind vane, which measures wind direction. These are actually pretty poor measurements because the wind comes through the rotor plane, gets altered before it actually gets measured. And also these sensors only measure at one point in what's now relatively large rotor plane. So these measurements are typically only used for supervisory control purposes. Now, the three main actuators on wind turbines include the yaw drive, which is usually available on commercial wind turbines and is used to try to actively yaw the turbine so that it's always facing into the wind. There are also these pitch actuators that pitch the blades, typically pitching the blades in high wind conditions to allow more wind to go by. And then there's also the generator torque controller. That's the hardest one to explain. So I'll explain that a little bit more on this next slide. So there are two main operating regions for wind turbines, and I'm going to try to explain these in the context of a 2.5 megawatt wind turbine example. So here we're plotting power as a function of wind speed. And the power available in the wind for a turbine of this size is given by this gray-blue curve, and it's a cubic function of wind speed. And the dark green curve shows the ideal power production we'd like out of this turbine as wind speed increases. So for very low wind speeds, due to friction and bearing losses and such, it's not considered worthwhile to be operating the turbine. Only when we exceed a particular threshold do we move into region 2 operation, and this is also called below rated operation, because in this region, the power being produced is lower than the rated power of the turbine. So the control goal in this region is to maximize power capture, to try to operate at maximal aerodynamic efficiency. So this portion of the curve here is also cubic, and essentially we're trying to maximize the fraction, maximize this power coefficient, maximize the fraction of the available power in the wind that we're capturing and hence producing out of the turbine. And so the controller and the actuator that's primarily active in this region is that generator torque controller. The generator torque controller essentially tries to decide how much power to pull off the turbine to put on the utility grid. If it pulls off too much power from the turbine onto the grid, then it's going to slow down the turbine too much. If it pulls off too little power from the turbine onto the grid, then it's going to let the turbine rotate too quickly. And there's some optimal aerodynamic efficiency point that we want to be operating at in region 2. Now, when wind speeds increase even further, then we move into region 3, and sometimes this is also called above rated operation, because at this point we have enough wind that basically as we enter into region 3, we're already at the rated power of the turbine. So the main control goal here is to regulate the power at the rated power of the turbine. Now, additional goals in region 3 are to mitigate structural loads. So the controller that's most active in region 3 is the pitch controller, where typically it's pitching the blades more and more to let more wind go by as wind speeds increase. And since there are 3 pitch actuators, we can try to meet additional control goals of trying to mitigate structural loads in high wind conditions. Now, the wind that comes into the turbine is usually highly turbulent. It's never perfectly uniform across the rotor plane. They're typically higher wind speeds higher up, lower speeds lower down. So this is kind of a usual kind of profile that we might see of wind coming into the turbine. So the wind impacts the turbine. The main quantity that's actually measured and fed back is usually the rotor speed. Now, in low wind speeds, we're in region 2, the torque controller is active, and it's trying to effectively indirectly control the rotor speed to be operating at the maximal aerodynamic efficiency point. Now, as wind speeds increase and we move into region 3, the pitch controller becomes active. Now, essentially, the torque controller is just regulating the torque at some rated torque level, and the pitch controller is trying to regulate the rotor speed at some desired rated rotor speed level. And the goal is that that constant torque times the constant rotor speed will equal to the rated power in region 3. Now, this is the typical control of wind turbines that's on commercial turbines, and it's primarily feedback only control. Now, a lot of my group's work over the last decade has looked at augmenting the feedback controllers with a feed-forward controller, where we try to use additional sensors to measure the incoming wind. So I've worked with remote sensing scientists and their groups to investigate whether we can use LiDAR sensors, which could be mounted in the hub or on top of the nacelle, and it scans ahead of the turbine and allows us to have preview information of the incoming wind. And we can use that information in addition to the feedback information available to develop combined feed-forward feedback controllers that lead to better performance in both maximizing power capture as well as regulating power in above rated conditions. Now, I pointed out the wind vane earlier. The wind vane measurements are typically averaged over minutes, often like 10 minutes averages, that are then used to determine whether there's a yaw error, and that then feeds the yaw controller to try to yaw the turbine to be facing into the wind. Now, LiDAR measurements also give information about the wind direction, arguably much better wind direction information than the wind vane, and so the LiDAR measurements can also improve the yaw control. So I kind of wanted just to give this overall view of some of the work that we've done in combined feed-forward feedback control of wind turbines. But that's not the main focus of this talk. In this talk, I'd like to highlight a large interdisciplinary project that we've had the privilege to be a part of. We're trying to design kind of a new concept wind turbine at a very large scale. We ended up having to kind of work very closely together as a large team, and we developed what we call this aero structural control co-design approach to really kind of optimize the design and control of this novel concept turbine. So I'll talk about some field testing that we've also done for the novel concept turbine, and I'll talk about a control approach that we're developing that helps us to reduce the cost of wind energy. Then I'll summarize, and as there is time, I might briefly outline some areas of ongoing and future work. So the earlier discussion on wind energy, I guess the main points there is that the wind industry generally is doing pretty well. Now, this pandemic has thrown a wrench into the wind industry as well as many other industries, but hopefully the wind industry will continue to do well. And the other main point of that earlier discussion is that there's still a lot of room for growth for the wind energy industry, and in particular for US wind energy. So what the wind industry has continually tried to do as it competes with other sources of energy is to try to continue to drive down the cost of wind energy, to try to drive down what we call this levelized cost of energy. And this LCOE is equal to the sum of the costs over the lifetime of a power plant. And so this could be a wind farm, it could be a natural gas plant, whatnot. And the denominator is the sum of the energy produced over the lifetime. And so LCOE is used to compare the cost of one type of energy with another type of energy. So in the numerator, the costs include the capital expenditures. So how expensive is it to build that wind farm? How expensive is it to build that natural gas power plant? Also included in the numerator are the operating expenditures. How expensive is it to run the wind farm? Now, included in the operational expenditures are the fuel costs, which happen to be free for wind, solar, and hydro. It's not free for fossil fuel-based power plants. In the denominator, we sum the annual energy produced over the lifetime of the power plant. So what we want to try to do is minimize the numerator and maximize the denominator. Now, usually in my past work, and for most of us on this large project team, we've never really considered levelized cost of energy. The way things have always been translated to us for control systems engineers is in region 2, we want to try to maximize power capture. In region 3, we want to try to regulate power capture. And as we've better understood kind of the overall goal of trying to reduce the levelized cost of energy, that has also opened our eyes to maybe try to do the control in better ways. And I'll briefly touch upon that later. So how has the wind industry largely tried to drive down the levelized cost of energy? It's largely done so by going to larger and larger wind turbines. And as it has gone to larger turbines, that levelized cost of energy has generally trended downward. Now, the typical wind turbine size these days is ranges from 3 to 5 megawatts, kind of the most popular sizes that are installed. So a 5 megawatt turbine typically is 100 meters at hub height and has approximately 60 to 65 meter long blades. Now, when you see a wind turbine off in the distance, it's hard to really appreciate just how large it is. And so I like to compare these, this kind of rotor size to the Boeing 747 and an American football field, including the end zones. So these 5 megawatt turbines are really large, complex machines, and they have to be designed and controlled appropriately. Now, there are already commercial turbines that are even larger. So land-based turbines, you probably won't see larger than 5 megawatts, and because there are really very difficult transportation constraints over land at sizes beyond 5 megawatts. Offshore, there are fewer transportation constraints, so you do see larger turbines already. So there are 6, 7, 8, even 9 megawatt commercial offshore wind turbines. So Vestas has a 9.5 megawatt turbine that's already in commercial operation at some different sites. And that turbine has over 80 meter blades. General Electric also has the Haliade X. It's a 12 megawatt turbine. You can already order that turbine. It's not quite in commercial operation yet, but those turbines have over 100 meter long blades. And there are even larger turbines that are in development. So why do larger turbines lead to lower LCOE? Well, the main reason is that the power is proportional to the rotor area and the cube of the wind speed. And as I mentioned, there's generally higher wind speeds higher off the ground. And so by having a taller tower, you can access those higher wind speeds, and you can also put a larger rotor on the wind turbine when you have a taller tower. So that's sort of what's driving going to larger and larger turbines. But can we continue to upscale? Is there a limit to this? This is a figure from a series of studies done at Sandia National Laboratories, where Todd Griffith led these studies. They were considering 13 megawatt turbines with approximately 100 meter blades. They did an initial design where they just did an all fiberglass blade design. It ended up being really massive. Then through a series of innovations, including advanced materials, they were able to drive down the mass, and their final design, their best design, is down here. But even at this best design, it's generally believed that for upwind turbines, the blade mass is going to grow at least quadratically with the blade length. And that's one of the challenges as you go to larger and larger turbines, is you're going to have these very massive blades. So in our novel concept turbine that we're trying to develop, we are going to compare our results to this best design out of the series of studies. And so we're going to call this the Connor 13, the conventional rotor design at 13 megawatts. So our concept that we're trying to develop is a 2-bladed, downwind, very lightweight rotor. We're bio-inspired by palm trees, which are lightweight. They do morph with the wind, downwind, and they can survive hurricane conditions. And so we want to develop wind turbines that could survive, say, off the coast, off the Atlantic coast, where there are hurricanes. So we call our concept a segmented ultralight morphing rotor, or SUMR. So I'll be referring to the SUMR 13 as a 13 megawatt SUMR. And so the idea is that when you have a conventional upwind rotor, right, the net gravitational centrifugal thrust creates this kind of downwind load on the blades. And so as the blades rotate, you really have to worry about whether the blades might strike the tower. And to prevent that tower strike, these blades have to be kept stiff as they get longer and longer. And that's what's really driving that at least quadratic growth in mass of the blades as a function of blade length. So then you end up, as you get longer and longer blades, you end up with these really massive blades. There's a lot of material that goes into it, so that the capital expenditures is high, and it's also very expensive to transport and assemble these massive turbines. And so our idea is that as we go to larger turbines, what we want to do is consider downwind configuration, where then we can use much lighter weight blades. By having lighter weight blades, these are then very flexible. They can also morph with the wind. They can align with essentially these loads along the blades. And so then that then mitigates the structural loads. We can actually encourage this downwind morphing by actually having some downwind coning in how the blade attaches to the hub. And so the idea then is, in light wind conditions, the rotor is relatively wide open, maximizing power capture. As wind speeds increase, then the blades will kind of morph downwind, aligning kind of with this downwind load, and that will reduce structural load on the blades, and also naturally kind of try to regulate the power, because as wind speeds get higher, then that capture area reduces, and we're reducing power capture, trying to regulate power. And so we're also exploring some additional concepts that are more coming into the phase 2 of the project now. And so in phase 1 of the project, we were really trying to develop and demonstrate the downwind, really lightweight and load aligned with coning aspect. And so what we did as a team is we developed a number of these two-bladed downwind rotors, and we initially followed what is typically the traditional wind turbine design process, where usually the aerodynamical design of the rotor is done first, and then the detailed structural kind of layup of the materials in the manufacture of the blades is designed next. Usually by the time the control systems designers get involved, the wind turbine is essentially already designed. And we're just asked to develop the best controller that we can for this wind turbine, usually to try to maximize wind power capture in region 2 and try to regulate power capture in region 3. Now, it turned out that we had set in this overall project with ARPA-E, the funding agency, we set some pretty aggressive milestones. And we had a very aggressive milestone in year 2, where we ultimately felt we had to work much more closely together and improve our kind of iterations. And ultimately, we ended up with a design process that looked a little more like the following. So initially, we did kind of that sequential design process, came up with an initial SUMR design. We developed a controller for it. Then we evaluated the wind turbine system in relatively high fidelity simulation, where we evaluate a number of different wind conditions through what are called design load cases, different types of turbulent wind conditions, realistic wind scenarios. We assess the annual energy produced and the structural loads, and this performance we can feed back to improve the controller design, improve the tuning of the controller, and the performance is also fed back to the aero and structural teams to iterate on the turbine design. Now, most of us working in this aspect had never used levelized cost of energy as a performance metric in the past. But here, since being funded by ARPA-E asked us to have a very aggressive LCOE goal. And so we worked with collaborators at NREL, where they have detailed cost models. They can take the turbine design and the performance that is actually demonstrated through detailed simulations, and they can come up with a relatively accurate estimate of the levelized cost of energy. And so then this is fed back and we iterate. Now, our year one go, no-go milestone was to reduce the rotor mass by 25% relative to that Connor 13 design. And that we were able to do using that sequential traditional turbine design process. And our year two go, no-go milestone was to reduce the LCOE by 25% relative to the Connor 13. We thought, and when we set out these milestones, we thought reducing the rotor mass by 25% should get us, most of the way there in the LCOE reduction. Turned out that was not the case. So at the beginning of year two, when we did that detailed cost modeling analysis with our NREL collaborators leading that effort, it turned out that that 25% reduction in rotor mass only led to about a 5% reduction in LCOE. And then we all got pretty nervous that we were not going to meet our year two milestone. And so what we did is we kind of integrated together, worked much more closely together, developed estimates, simplifications and modeling that allowed us to assess many more designs more quickly. And so my PhD student, Dan Zalkine, and I kind of led this study where we did a number of trade studies. We came up with harmonic model analysis, a number of simplifications where we could evaluate many designs more quickly. So after the first detailed 13 megawatt design, which we call SUMER 13A, so it had about 100 meter blades and a downwind Coney angle of 5 degrees. So in size, it was about the same as the Connor 13, except it was more lightweight. So we had that 25% mass reduction. Then we wanted to vary a number of parameters and see if we can improve relative to the SUMER 13. So everything here is going to be normalized to the SUMER 13A. We're going to look at, can we increase annual energy production while keeping the structural load below where it was. And in initial studies, what we found is increasing that annual energy produced is the biggest factor in being able to reduce this levelized cost of energy. And so we varied blade lengths, and we found naturally that as you increase blade lengths, you're going to increase annual energy produced, but you're also going to increase structural loads. We also varied what's called axial induction factor, and at the same time we increased blade length. So the axial induction factor, if you will, is a greediness factor. It's a when it's set to 1/3, then the wind turbine is designed and controlled to be as greedy as possible. And that's the usual axial induction factor that's used. And if we reduce that greediness factor, which we did here, if we reduce it by itself, what it'll do is reduce annual energy production and also reduce structural loads. And so what we did is we decrease axial induction and at the same time increase blade length to try to keep that power production up. And what we found is we could do the combination of decreasing axial induction and increasing blade length such that overall we're increasing annual energy produced while keeping the structural load below this unity line. And so that was really exciting to us. Now, we also evaluated different cone angles. We evaluated both upwind configurations as well as downwind configurations. The focus of this project was of the RPE project was on downwind configuration. So looking at the downwind configuration, if we increase that downwind Coney angle up to 20 degrees, we can reduce the structural loads by almost 30%, while only giving up less than 8% of annual energy produced. So that to us was a worthwhile kind of trade-off. So we took all these things together. So these small dots are the different configurations that were evaluated using our simplified modeling techniques. And we put all these things together and then made a recommendation that the next detailed design we go through should have 125 meter blades, axial induction factor of 1/5, and a downwind coning angle of 12.5 degrees. And then as an entire team, we did this detailed what we call SUMER 13B design. And we did the detailed simulation evaluations and did show that we were able to increase annual energy production by more than 10% while not increasing structural loads. So then at this point, we felt confident we could meet our year 2 go, no go milestone. So we continued to iterate, varying blade lengths, assessing effects on the blade mass. In this overall study, we considered both two-bladed and three-bladed configurations, upwind and downwind configurations. But our focus on the RPE projects is two-bladed downwind. And so our final design that we recommended to do in detail, which is what we call SUMER 13C, had 145-meter blades, axial adduction a little bit greater than 1/5, and we preserved that downwind Coney angle of 12.5 degrees. And this is what led us to meet our year 2 go, no go milestone. So we essentially did kind of this aerostructural control co-design, and we iterated on the design of the 13 megawatt turbine until we met our 25% LCOE reduction. So we increased the blade length quite significantly. That's what allowed us to really increase the annual energy production, so by about 34% relative to the Connor 13. And it's this increase in annual energy production that really drove down that LCOE by 25%. Now you might ask, well, we increased the blade length by so much, haven't we increased the CapEx? Yes, we have increased the CapEx, but not by that much. It turns out that CapEx typically is about 75% of the numerator, and that the turbine CapEx is about 1/3 of the overall CapEx. And the blades are only part of the turbine. There's also the nacelle, the generator, the tower. So the blades, by increasing the blades this significantly in length, we actually only increase the overall CapEx by about 7%. And so it's really that increase in AEP that really allowed us to drive down that LCOE. So this was really exciting to have met that goal. So this balance of station, you might wonder what that is. That includes, for land-based turbines, all the concrete for installing the turbine, includes the cabling, how do you transmit the power from the turbine onto the utility grid, etc. And that does end up being quite a significant chunk there. All right, so in many aspects of this project, which I won't have time to go into, so let me just highlight the major points. We did our first detailed 13 megawatt design, which we called SUMER 13A. And we actually aeroelastically scaled that down to approximately 21 meter blades because we wanted to manufacture those blades and actually demonstrate this concept in experimental field testing. Now, while those blades were being manufactured is when we did our aerostructural control co-design iterations to try to meet our LCOE goal for year 2. We've also scaled upwards and have done a series of 25 megawatt designs and a series of 50 megawatt designs. And here we're getting to more than 250 meter blades, really, really extreme scale. So I don't have time to go into the details of all of this, but I would like to highlight some of the main points on our field testing. So full disclosure, we actually had many more detailed designs than those three designs. We had multiple SUMER 13As, if you will, and the particular one that we scaled down is what we had called SUMER 13I. So it had 104.4 meter blades, and we scaled down to 20% scale. And if I labeled on, this is 20% scale, but if I labeled on here, you won't be able to read it. So I'm just going to label it on a larger one. So we had about 21 meter blades and we preserved that 12.5 degrees of downwind coning. Now the 13 megawatt designs were designed for an offshore site off the coast of Virginia, where there's kind of medium winds, medium turbulence levels. So for this SUMER demonstrator, which we're calling SUMER D, we're actually field testing at the National Renewable Energy Lab, so at NREL, and there they have very high wind conditions and very high turbulence levels. So we actually had to do some control co-design iterations at the SUMER D scale to ensure that the blades that were manufactured would survive the NREL site conditions. So this is a video of the NREL site. So around here, mountains are west, and Boulder is El Dorado Canyon, and the dominant wind direction is coming from the west. So the winds come through El Dorado Canyon onto this site. So these two medium scale turbines, they're about 600 kilowatt turbines, are Controls Advanced Research turbines. My team has had the privilege of being able to test some of our advanced controllers on these turbines. The two-bladed platform is the one we used for the Sumer D. And so we took off the blades that were on the Cart 2, replaced them with our new blades. So this control shed, as it's called here, we can see the Cart 3 out one window and the Cart 2 out the other window. The real-time control system is implemented in LabVIEW and operates at 400 hertz. Now, the blades are actually manufactured by Janicki Industries, which is located in Washington State. And I don't have time to get into the full details of the manufacturing process. We also had to, Cart 2 is normally an upwind turbine. We had to configure it for downwind operation, and many details had to be sorted out to make that work properly. We also had to design and manufacture an adapter plate in order to mount the blades with that 12.5 degrees of downwind coning. Ultimately, there were many issues that arose, even though this is 20% scale. When you have 21-meter blades, it's still a pretty large experiment, and a lot of little things can go wrong. And ultimately, it took us a full year to get to operational field testing. And so the blades sat on the turbine in a parked state for quite some time. And this video here is showing, so even when the wind's blowing, the turbine will rotate. And the main thing I want to show with this video is just how flexible the blades are. So if you look closely, you can see just how flexible they are. So we did get into operational testing finally. And this video was taken maybe about 3 months ago before we went to shelter in place. And you can see that it is downwind relative to the other turbines nearby. And you can see that downwind coning. So we're now, after we went into shelter in place, our field experimenting has slowed down quite a bit, but we have been busy analyzing the data that we have collected. I don't have time to get into full details here, but just want to point out that from the controls point of view, one of the things we worry about is trying to control the wind turbine in such a way well enough that we don't have generator speed peaks that are too high. In particular, we don't want to cross a particular threshold here, where if that threshold is crossed, the turbine will actually automatically go into shutdown mode. And we definitely don't want that to happen, because then we'll really lose a lot of annual energy production if that happens too often. And so we have hundreds of periods of operational data that are plotted by these blue dots. And what's actually plotted is the peak of the generator speed over those operational periods. And out of those hundreds of periods, there were 2 occurrences where it did cause a shutdown. So we're analyzing those cases more closely, looking at the wind conditions that caused them. We're also trying to reproduce the field results in simulation. So we're trying to reproduce the winds. So there are a lot of details that we're trying to work through. But let me move on in the interest of time. So one of the controllers that we have tried to develop is what we call a load-constrained power control. And here we're trying to think, again, more broadly, beyond the usual maximize power production in region 2, regulate power in region 3, and looking at, well, we're really trying to reduce this levelized cost of energy. What more can we do with the control to increase that levelized cost of energy? So we're trying to look beyond the existing controllers. And what we decided, especially looking at all of the data in terms of our detailed simulations of the Sumer rotor, what we wanted to do is basically assess if, what we really want to do is never cause the turbine to go into shutdown mode. So we don't want to, for instance, exceed this maximal generator speed constraint. There are a number of other constraints on different loads that we don't want to exceed. So essentially what we want to do is assess if we're in kind of a safe region, we can then maybe be a little greedier and try to capture more power. If we're in regions where we're thinking we're getting close to the constraint boundaries, then we want to actually pull back and try to even derate, generate less power so we don't get close to those constraint boundaries. And so So this is just one set of time series. The wind is turbulent wind. On average, the mean wind speed of this wind series is a little under 15 meters per second. The actual rated wind for this 13 megawatt turbine is a little above 10 meters per second. So what we see is in the beginning and the end of the time series, we're in region 3, so the generator torque is saturated, the blade pitch is active. In this middle region, we're actually in below rated wind, so the pitch is saturated and the generator torque is active. And usually what's translated to us control engineers is they take the absolute generator speed constraint and they artificially lower it by some amount, usually about 20%. And then they tell the control engineers, please design a controller to regulate the generator speed about this rated generator speed. And if we do a good job, then it's very unlikely we'll ever exceed that generator speed constraint. But now that we understand if this is the real goal, where you don't want to exceed that generator speed constraint, then we can try to be greedier, allow the generator speed to be a little bit higher at times and possibly capture more power in those times. And then in kind of dangerous times where we're getting close to the generator speed constraint, then we try to pull back and generate less power. And so we want to try to, reduce the peaks on the thrust and the blade loads, try to reduce the structural loading. So this actually wind time series is considered a relatively difficult one, where there's a lull in the wind, so we move down into region 2, and then the wind speed rapidly picks up. And oftentimes then the blade pitch maybe can't keep up, and we end up, getting reasonably close to that constrained boundary, and we see these peaks in the loads. And in fact, the two conditions on the SUMR-D data where we did exceed that generator speed threshold looked something like this if we look at the wind speed data. So essentially what we want to do is we want to try to boost the power where possible, but then we want to look at the turbine measurements, assess, and determine, are we near the constraint boundaries? Somehow it's not showing up, but are we near the constraint boundaries? And we basically want to pull back if we feel we're near the constraint boundaries. We also want to assess the wind situation. So we can use the turbine measurements to estimate the wind speed, or if we have wind speed sensors, we can use those measurements directly. So either way, we have some assessment of the wind situation and we can derate based on that situation. So I don't have time to get into the details, but I just want to show the results here. So the gray lines are what we had before, kind of that constant generator speed, kind of artificially lowered set point that we're trying to regulate to. And so the blue curves are what we had before, the existing controllers. The red curves are now with this load constrained power reference controller. And what we see is that in the beginning and end of this time series, we are trying to be more greedy. So we see the generator speed is also higher there. And in this middle region, we've assessed that things are difficult. And so we're actually pulling back and we're actually reducing the power. This power set point is actually lower than the original power set point. And so we're capturing less power here, but overall, on average, we're actually capturing more power. And we see that we're actually able to stay further away from the generator speed constraint. And overall, we have lower peaks in our structural loads. And so this is really exciting to us because we kind of have win-win. We're able to capture more power and reduce structural loads. And we've developed this controller further over the last year, and we're actually about to submit a journal submission. Dan Zalkine, my PhD student, actually used this control approach as the basis for his entry in the ARPA-E Atlas floating offshore wind turbine control challenge, and he ended up winning the $100,000 first prize. And so that was really exciting. So he actually officially graduated last week and officially started working as a research engineer at NREL yesterday. So I'm sad to see him go, but hopefully we'll continue to collaborate. So in summary, this working together very closely as a team allowed us to do better design of rotors that can lead to lower levelized cost of energy. Doing field testing is very, very challenging, but it's also very satisfying once we have gotten now to a successful field testing. And this load-constrained power control idea, we think, is a good approach to further minimize the levelized cost of energy further. We definitely developed the controller from an applied point of view. We're now trying to establish some theoretical guarantees on the performance. As I mentioned, our overall project originally was 2016 to 2019. That was phase one of the project. We were invited by ARPA-E to submit a cost extension proposal, which we did, and they've now funded this. And we're now focusing at the 25 megawatt level, and we've added General Electric as a partner in this project. We are designing and evaluating 2- and 3-bladed downwind rotors, also including segmentation of the blades and including outboard flaps on the blades. And from a controls point of view, we're hoping to control these flaps to further alleviate structural loads on these really extreme scale turbines. Now, just to highlight a few areas of other wind energy work that is becoming very popular in the research community. One is control of wind farms. And here, wind turbines interact with one another through their wakes. So this is a now relatively famous photograph of the shallow water offshore wind farm off the coast of Denmark, where as the wind passes through this first row of turbines, you can see these wakes develop. Now, the wind speeds are lower in the wakes, and they're also more turbulent. So these rear turbines see lower wind speeds, so they can't generate as much power. They also get beat up more structurally because they're seeing more turbulent winds. So we're trying to understand these wake developments, the wake interactions, and then what we want to do is take into account that information and coordinate the control of the wind turbines to improve the wind farm level performance. And it turns out you can actually improve the wind farm performance quite a bit. So the usual way that wind farms are controlled is to have each turbine controlled as greedily as possible. So this is what we call a locally greedy approach. So every turbine is facing the wind, and each turbine is trying to be as greedy as possible. Now, in some of our earlier work here, we used past data that had been collected by other groups and developed a steady state wake model where we accounted for yaw errors. And it turns out you can actually yaw the turbines to steer the wakes behind it as much as possible out of the way of that next turbine. And so we developed this steady state wake model, applied it in solving for the optimal yaw settings, and it turns out that we overall can generate 13% more power than every turbine being as greedy as possible. And on average, we actually see reduced loads, because what happens is by steering the wake out of the way as much as possible, that next turbine sees mostly free stream air, or free stream wind. And that free stream wind is higher in speed, and that leads to the increase in power capture. But that free stream wind is also less turbulent, and that's what leads to, on average, reduced load. So again, this is exciting because we have that win-win situation with more power production, lower loads. And so these were very high fidelity simulations using NREL's SOFA tool, the simulator for offshore wind farm applications. So this is now a very popular area of work in terms of wind farm optimization. There's a lot of work still to be done. We only developed a steady state wake model. There are now dynamic wake models that have been developed that are relatively accurate. Now, to actually implement wind farm controllers in practice, we need to have good measurements or estimates of the wind speeds throughout the wind farm, and that's a challenge. You could use more LiDARs across the wind farm, but that can quickly get expensive. So I have two students working in this area looking at kind of low-cost solutions. So Michael Sinner, my PhD student, is just used what I refer to as very poor anemometer and wind vane measurements. They're available on commercial wind turbines, so they're readily available. So can we use those measurements, incorporate a simple dynamic model of the wind field, and use a Kalman filtering approach to estimate the wind speeds? We applied this on actual wind farm data. The gray shows the raw measurements, and you can see there's definitely some spurious measurements which we think are actually faulty. And the green measurements are the result of our Kalman filter estimates. We believe that these are better estimates, but this is from an actual wind farm, so we don't really know what truth is. we're hoping to convince the wind farm operator to allow us to test a wind farm controller on a subset of their wind farm, in which case we hope to show increased power production. Now, another student, Dave Pasley, is really interested in using UAVs, which have wind speed sensors, pressure, humidity sensors. And so then the question is, can we fly these UAVs through information-rich areas of the wind farm to gather data and allow us, in a relatively low-cost way, to come up with good wind speed and direction estimates. And initial results are very promising, but there are many open questions that we're still trying to resolve here. Now, I mentioned earlier that some of the best winds around the US are just offshore. And right now there's only one small commercial offshore wind farm. So there's really a lot of area for growth for offshore wind in the US. One of the challenges in the US is that nearly all of the West Coast and some portions of the East Coast, we have deep water. So 99.9% of existing offshore commercial wind farms are in shallow water, where the wind turbines are built all the way down to the seabed. So around the US, most locations are going to require deep water. And here, economically, it does not make sense to build the turbine all the way down to the ocean floor. So we're really then talking about floating offshore wind turbines. And so here, think of an inverted pendulum with this huge rotor at the top, affected by the wind and the waves. And so there are definitely many control issues. One of my students has done an initial controllability and observability analysis, looking at several typical floating offshore configurations that have been considered, where there are research turbine platforms out there. And so looking at how much control energy is needed to kind of move back to that vertical position from different offsets. And there are some directions where we require more control energy. Now, the existing research turbines that are floating use floating platforms that are largely borrowed from the oil and gas industry. So they tend to be relatively massive and heavy. And we have a new project funded by ARPA-E, which literally launched on May 1st. So we're just getting started, where we're trying to apply and extend that control co-design approach for floating platforms. Can we design lighter weight platforms targeted for wind turbines, where we can reduce the cost of these platforms and where we can still guarantee stability of the floating platform. So here, Katie Johnson and I are the control systems researchers in this project. We also work together on the SUMR project, and we jointly are seeking a postdoc. And we actually posted an ad in the Control Systems Society e-letter. If you're interested or you know of anyone who's interested, please encourage them to apply. The main background was we're looking for someone with control systems background. If you have wind energy experience, that's a plus, but it's not required. All right, one last area I just want to point out is active power control of wind turbines. And this is, again, an area where we're trying to get away from the usual maximize power production in region 2, regulate power production in region 3. Because as we get to higher and higher wind penetrations, 20, 30, 40%, maybe the grid can't take all that wind. Maybe what we need to do is think about things from the grid perspective. Maybe that transmission system operator from the utility grid will tell us how much power we need to be producing from the wind turbine. So if we take, say, a 550 kilowatt platform, we derate by 10%, so we're normally operating here, then we could increase or decrease power as the grid needs require. And so we developed a new controller to essentially control the power production of a wind turbine, and we tested it out on the CARP3 platform at NREL and showed that we could follow the power reference relatively well. And of course, there are natural extensions to wind farms. So the point of pointing out all these different areas is to say that even though many people say that the wind industry is relatively mature, there's still many areas of challenges, many opportunities. And I was lucky enough to be part of this large group where we met regularly over about a year and a half discussing the major challenges in wind energy, and we came to some consensus of several areas that we called grand challenges in the science and engineering of wind energy production that we think should be addressed over the next 3 decades or so. And so to close, I'd like to acknowledge ARPA-E and NREL for their support of this research. Envision Energy has also supported some of our wind energy research in recent years. And I've been lucky enough to have some discretionary funds which has allowed my group to really go after some radical ideas. Some of these have worked out well, not all, but it's fun to be able to try. The SUMR team has been fantastic. I don't have time to point everyone out. I do want to say that Katie Johnson and I hired Chris Bay as a postdoc jointly a few years ago on the SUMR project. He actually had no wind energy experience prior, and he worked out excellently, and he's loved wind energy. He's actually now working full-time at NREL. And Dan Zalkheim, my PhD student who just graduated and also started working at NREL. So this is the most recent group photo we have. It's already a little bit outdated because Dan here has already graduated, and I have a new student, Mandar Fadness, who has started in January, doing an excellent job in filling the relatively large shoes that Dan has left. And so, sorry to go a little bit over. Thank you for joining and for your attention. I'm happy to answer any questions.
Thank you very much. And yeah, so we can have questions. If you have any questions, please type them in the chat window. I think we already got a few questions. Let me actually start by asking one question myself. I was wondering, when you mentioned the evaluating the design space in the beginning, that you had major computational gain in that, was the gain mostly from, let's say, a more efficient simulation algorithm, or was it, for example, reduced modeling or using reduced models?
Reducing, yeah, so using reduced models. We did a harmonic model kind of analysis where just by looking at the first few harmonics, we're able to have a pretty good assessment of the structural loads. And so it was a really simplified model analysis in order to examine a larger parameter space quickly. There is, you know, as we were talking before the seminar, we are starting to look at some data-driven approaches, and this is an area that I'd love to talk with you more about, since we're not data science experts, and how best to take that information and come up with efficient ways to drive our designs.
Yeah, that would be definitely very interesting. Okay, so in the chat window, there was one question that is asking, is there a reason that wind vanes can't simply be placed in front of the wind turbine? What would be the problem with sticking out a straight bar through the nose of the turbine and putting the wind vane there?
And that's a great suggestion. So it turns out, so certainly as the wind comes through the wind, you know, the rotor plane, it gets altered before the wind vane. But the wind actually starts to change even before it hits the wind turbine. And so even placing the wind vane out the front will not lead to very accurate wind speed measurements. You really need to be, you know, quite a bit in front of the turbine. And so right now, you know, we're running that Part 2 in downwind configuration. We do use the wind vane information, which is now upstream, but it's also still not very accurate because it's too close to the rotor plane.
Okay, another question is, to what extent does the flexing of the blade affect the aerodynamic efficiency? This is from Daniel Kirshen.
Yeah, that's a great question. That definitely has some effect. We do not actually have a complete answer on that. That's something we're trying to analyze from the field data on the SUMR-D. And yeah, that's a great question. It's not clear. It definitely has an effect, and that's something we're trying to assess. And that's an open question in terms of whether this concept really will be viable.
I see. And then another question, what are the disadvantages of downwind turbines? Why aren't there more of them on commercial operation? So
in the early days, when it's downwind, usually there's a little bit more noise, okay? Because so when you have an upwind configuration, the wind comes through the rotor first before going around the tower. In the downwind configuration, the wind will go around the tower before going through the rotor plane. And so it usually then is just a little bit more turbulent before going through the rotor plane. So as that, as the blades chop through that slightly more turbulent area, that leads to more noise. And so that has been a drawback for downwind turbines. It's not really considered for land-based turbines. So for offshore is where this is being considered. And also the advantage in our design is we have that downwind coning, which makes the blades, in particular the tips, further away from the tower, which reduces the noise effect.
Another question is, let me see, what are your safety margins as you're incorporating flexible components that tend to push safety margins?
Yeah, so we definitely have built in safety margins, certainly for the Sumer D. We have different safety margins for different components, and they vary from 1.5 to maybe 2.8, I think was the range of safety margins, if that makes sense to you, in terms of how we designed the Sumer D blades. And so far, knock on wood, so far things have worked okay. And the blades sat on the turbine for about a year before we finally got into operational status. And the NREL wind site does see howling, 100-mile-per-hour winds throughout the winter time. So it has sat out there for 2 winters now. So knock on wood that we continue.
Yeah, John, if I can continue for a minute on my question here. I don't know if you've seen Michael Moore's new movie, Planet of the Humans, which attempts to drive a stake through the heart of wind power. And it all really narrows down to this issue of lifespan. That the wind systems take huge amounts of resources to make. Wind turbines are not a renewable resource, even though the wind is. And if you do the math on this is not something that can go on long term unless the systems basically last pretty much forever. And you need much larger safety margins for things that last centuries and not years.
Yeah, that's a very good point. So it turns out that wind turbines have generally lasted longer. So oftentimes they're designed to be 20-year lifespans, and oftentimes they do end up lasting for 30 years, possibly more. They are now being manufactured more and more. This is a big research area with recyclable materials. You're right that for a long time, wind turbines were not manufactured in a recyclable way. And that is a big issue now as wind turbines come to end of life. But wind turbines are more and more being manufactured with recyclable materials. Yeah, it's you raise a good point. And there's, obviously from the wind industry point of view, they're ultimately trying to make some profit, right? So it's this trade-off of having infinite lifespan versus having some profit margin. So there's a lot of competing objectives. But I think that we can go to longer lifespans, and that they are now being manufactured with more recyclable materials.
Okay, so thank you very much. We are out of time now, even though I think there are even more questions coming in, but let's end here. Thank you so much for a great talk.
Thank you. Thanks everyone for joining.